So firstly, you have to know how to linearize by hand, manually linearize the system using Taylor series. So here for the autonomous system, the system without input, using the Taylor series, and you will have something like this. But as the operating point, the f operating point will equal to 0, and because it's very close to this point, so the higher order terms will equal to 0. So the system will be like this if you put at operating point, and also because it's operating point, so this part will equal to 0. You see? Here, they put very clear. So you have system like this, and because we put, it depends on your system is a continuous system or it's a discrete system, you can put this differently. So here, for example, here is continuous system, so you put something like this. So you have x dot equal to matrix A multiplied by x. So it's exactly like this. Dot something like this. That is y at capital equal to the data set. For the system with multi-input, multi-output, and even have a disturbance, you can put the same here. You can still use partial differentiation to put the same in the same principle. In the end, you have something like this. You take the partially differentiation of x, w, and here if you have w, you can put it. So that's it for the Taylor's linearization, manually linearization using Taylor series. So first, for linearization of a system, it's much better to put the system in this form. By putting the system in this form, you can know how many outputs you have in the system and how many states you want to have, because it depends on the way you form the system. You can have different number of states, different number of input u, and different number of disturbance, or what you call it, something else which you don't consider as an input of your system. Right. For linearization using Simulink, first you have to form the system to build your system in Simulink, and define the output with an out block and input with an in block. Yeah, so in the Simulink, in the top level, you will see something like this. So it depends on your input. Here, if you want also to see the effect of the disturbance and the input yield to the output, which you have this form. So in the end, you will have this form. This form, I v1, v2 can be a linear time variant, or can be a function of x, even u, and w. The same for C, D1 and D2. Some of your system might don't have disturbance, or you don't want to consider the disturbance into your system, you can remove this part. But in general, you have something like this. So first, you need to have a form like this with input. You can put U and W into one like this, because MATLAB only consider one set of input. Okay, the same for output. And this is a form of, I put it exactly like a form of here. So dot s dot here is equal to a function of u x w, and the same for y. So to linearize the system, you have to go using analyze it. Depends on your MATLAB version, you have to go to a library. But here 2017B, you go to analyze it, control shift, control design, and linear analyze. This is you have something like this. And firstly, you have to provide an initial point. Not exactly the operating point, but it's just an initial point for the system. So I prepared here. Not exactly the operating point, you can put anything you think is around the point you want to linearize. So here first go to operating point. We have to find an operating point before we can linearize the system. So using trim model. Okay, so they go automatically and adopt the point I put into the system, because here I use in this form. So in this integral, I put the operating x. So when we use the trim model tool of MATLAB, I will copy this value into the initial point here. You can okay. So now we have some option. So if any state you want to be a steady state, you stick this column. So everything is steady state. You can also define the input, like you already know some input, especially for the disturbance. So here I know I have one, for example, in channel. Yeah. Okay, so for I have 8 input and 4 disturbance. I already know the disturbance will be around this value, so I will put according to mine. And I want the output of the system. I know here I know some state of the system. I know this state, and now I will act around this state. So we put this around this value of that state. So I will fit this state, fit on the known column. Alright, so we fit the two state. Here in this actually is a system of two window bytes, and the equivalent the grid dynamic. So I know this state, I know this input. It's actually a disturbance, but the disturbance, you see, we put disturbance and input in the same form, because MATLAB Simulink, they don't recognize the system like this, they only recognize the A and B1. So here we have to put, so Simulink only recognize the system like this, A and B, C and D, not B1 and B2. So we have to reform this system into this kind of system. So now the input of MATLAB Simulink will be U and W. So you put the disturbance into the input. But then when you after you linearize the system, you can cut it out because it's very easy to cut it like this using some function in MATLAB for matrix manipulation. Okay, so we set the condition we need. You can set some minimum and maximum of state specification, and you also go to option to change the tolerance, to change the way the optimization methodology here. But for this system, is the best. Normally, it will be the best here. Gradient descent. Okay, so just start trimming. Okay, simple everything. You see, operating point specification was successfully met. So it's okay. You can check it again. I click on this. You can see here. This is the design. Yes, if it is steady state, it will be equal to 0, but the actual value here will be very small, but it's not 0. So it depends on your system. Maybe you have to set the tolerance even smaller than this. In my case, it's enough. So you will see here the state will be fit at this value, and we set here Okay, I can slide this and like it to be clearer for you. So okay, so state 10, state number 10 will be fit this this value. The same for state 20, the same. And the input here you see from number 9 to 12 we fix as it is. And we did here. We can click on no. We don't have condition for output, so I will put the output depends on that state. Right. So now we have to linearize around this point. Now we have the operating point. We go to here. So because we define the root level in input and outputs, it's here, as we did here. Inputs and outputs. So now it's easy because we just set it here. You can set the input output here like this, but this way it's not clear for you that you have how many output, how many input define. It's better to put it like this. And here, go to this one. You don't need to, if you want to see some step response, bow, figures, views, whatever. But in this case, normally you don't need that because it is multi-input, multi-output, so it's really hard to analyze the system based on step response, bows, and so on. From multi-input, multi-output, it's better to use model analysis in the next video. So linearize at this point because we operating point we set this one here. So linearize now. Okay, so here you see we have SIP output as exactly what we did. 12 input is actually 8 inputs and 4 disturbance and 21 state. Exactly like what we define. The number state doesn't change. Input, number of inputs and outputs doesn't change. Okay, so now how can you copy this value into the system? You have to copy this value into the MATLAB workspace. I click on this and put in MATLAB workspace. So now they are here, but it does for the linear system it's a state space, so you have to use state space here to state space data to copy it into the matrix. And for my case, I would want to copy into M5 to save it. So I copy into M5 to save it like this. So now it will save to the M5 linearized system here. And the next one for the operating point here. It's a set, so it's again you have to manipulate this to extract the operating point. So here I create a script. So it's kind of playing with object in MATLAB. So you have to test to see whether the value you want to extract is from which part. So in this case, it's from state. So I get it from the state, and just ds. So operating x will be from x, and it's in the form of this, because here it's kind of better, so you have to transpose it into another form to meet the design you want. The same for B1 and the operating input. Here I put the beta because it's the notation for the controlling the converter of the wind turbine. And here this stubborn, I notate it by W, so I put operating W, the same. So here, and this one I tell you, here I cut it out by using this. You see, from 1 to 8, here B1, and for the rest for B2. Okay. No, this one is for the here U, and this one is for the for the disturbance here. So for the matrix, it's inside the linearized system here. It's like this, matrix A, B, and in this matrix B, it includes B1 and B2. So you have to cut it from here, like this, or like this. Okay, so now we have the linearized system. So to extract the matrix B1 and B2, I will give you another thing. So first I will call the linearize file to put the matrix ABC D into the MATLAB workspace, MATLAB workspace, and then I will cut for matrix A is the same. Matrix B1 will be, you see, from the only for the first 8 value. So I will put like this to cut the B1 out. The same for B2, but will be the rest. So in this case, I remove one disturbance because it's a constant. So when you linearize the system, you have to so you can cut it out, because when you linearize the system, it's actually using the Taylor expansion. Okay, so same for matrix D. Because here I only D1 because I know matrix D, as you can see here, is 0. So I can put D without D. So D1 and D2 here, both of them are equal to 0. That's all for linearization. And then you can use this matrix to decide here I decide the H infinity for the system for the next videos. Okay. So that's all.